Hello everyone. Last time we were talking about limiting and non-limiting reactants and we discussed a couple of examples. Today we're going to solve few examples related to the same topic, that is limiting and non-limiting reagents. So the example from your book that we're going to solve today is example 1.6, and it states that 200 grams of potassium dichromate were reacted with 200 grams of concentrated sulfuric acid. Calculate A. Mass of atomic oxygen produced. B. Mass of reactant left unreacted. The balanced chemical equation is given here. So let me write it for you. Right, so this is the balanced chemical equation, and you can see that 1 mole of potassium dichromate reacts with 4 moles of sulfuric acid to produce 1 mole of potassium sulfate, 1 mole of chromium sulfate, 4 moles of water, and 3 moles of atomic oxygen. The question is about calculating the mass of atomic oxygen that is produced when 200 grams of potassium dichromate reacts with 200 grams of sulfuric acid, and B, the mass of the reactant left unreacted. So the very first thing in solution is to find out which one of these two is the limiting reactant. And you already know that we can find out or we can identify the limiting reactant from the number of moles of the reactants given to us. But we are not given the number of moles, we are given the amount of reactants in grams. So, what is the given data? We have 200 grams of potassium dichromate and we have 200 grams of concentrated sulfuric acid. So first of all, we have to convert the grams of both of these reactants into the number of moles. So you know that moles can be calculated from the mass in grams and the molar mass. So the number of moles of potassium dichromate would be the mass in grams, that is 200 divided by the molar mass. If you calculate the molar mass of potassium dichromate, taking into account the atomic masses of potassium, chromium, and oxygen, it is equal to 294 grams per mole. And from this, the number of moles are equal to 0.68 moles. So what we are given are 0.68 moles of potassium dichromate, and these are to be reacted with 200 grams of concentrated sulfuric acid. So first we have to calculate the number of moles of sulfuric acid, that is 200 divided by the molar mass of sulfuric acid is 98, so we divided by 98, and this is equal to 2.04 moles. Now we know the number of moles of both the reactants given to us, but that we calculated from the mass in grams given to us. Now we have to find out the limiting reactant among the two. So from the definition of limiting reactant, you know that limiting reactant is defined as a reactant that is present in lower quantity in terms of moles, or you can say that it's a reactant that is consumed completely during the chemical reaction, or you can say that it is a reactant that produces the least number of moles of or the least quantity of the products. But first let's see if we can find out the limiting reactant from the molar ratios given to us. So let's find out the limiting reactant, and that we can do from the balanced chemical equation. So from balanced chemical equation, we know that 1 mole of potassium dichromate reacts with 4 moles of sulfuric acid. So if we are given 0.68 moles of potassium dichromate, it will react with 4 into 0.68 divided by 1 is equal to, this would be equal to 2.72 moles of sulfuric acid. So for complete reaction with 0.68 moles of potassium dichromate, we would need 2.72 moles of sulfuric acid. But what we are actually given are 2.04 moles of sulfuric acid. So what is required are 2.72 moles of sulfuric acid, but what we have are 2.04 moles of sulfuric acid. So it is lesser than what is required for a complete reaction with 0.68 moles of potassium dichromate, which means that sulfuric acid is the reactant which is present in lower amount in terms of moles, because we need 2.72 moles, but we have 2.04 moles. That makes it a limiting reactant. Now let's see this from another angle. If we do the calculation from the number of moles of sulfuric acid, so from balanced chemical equation, we know that 4 moles of sulfuric acid will react with 1 mole of potassium dichromate. But if we have 2.04 moles of sulfuric acid, how much quantity of potassium dichromate would be required to react with it? So this is equal to 2.04 multiplied by 1 divided by 4, and this is equal to 0.51 moles of potassium dichromate. So for a complete reaction with 2.04 moles of sulfuric acid, which are given to us, we would need 0.51 moles of potassium dichromate. But what we are given are 0.68 moles of potassium dichromate that we have calculated from 200 grams of potassium dichromate. So what is the requirement? 0.51 moles of potassium dichromate, but what we have are 0.68 moles of potassium dichromate. So the requirement is less than what we have, or in other words, what we have is more than our requirement. So potassium dichromate is the reactant that is present in excess. We need 0.51 moles, but we have 0.68 moles. So this again proves that potassium dichromate is the excess reactant, or in other words, sulfuric acid is the limiting reactant in this case. So once you have decided, or once you have identified which one of these two is the limiting reactant, the rest is easy. Now, any calculation or any data that you need to calculate from the given question is to be calculated from the limiting reactant. So now we know that sulfuric acid is the limiting reactant. So we have to calculate, or we have to do the calculations from 2.04 moles of sulfuric acid that we have. So let's solve the first question. So the first part of the question is to calculate the mass of atomic oxygen produced. So again, you know that sulfuric acid is the limiting reactant, and we have 2.04 moles of sulfuric acid. So we have to do the calculations from sulfuric acid to calculate the mass of atomic oxygen produced. So again, from balanced chemical equation, we know that 4 moles of sulfuric acid produce 3 moles of atomic oxygen. And this is from the balanced chemical equation. But what we have in our hands are 2.04 moles of sulfuric acid, and that will produce 3 into 2.04 divided by 4, and this is equal to 1.53 moles of atomic oxygen. But the question is to calculate the mass of atomic oxygen produced. So you can convert moles into mass. So mass of atomic oxygen is equal to the number of moles multiplied by the molar mass. So number of moles is equal to 1.53 multiplied by the molar mass of atomic oxygen. This is not an oxygen molecule, it's an atomic oxygen. So we have to take the atomic mass of oxygen, that is 16. So 16 into 1.53 is equal to 24.48 or 24.5 grams of atomic oxygen. And this is the amount of oxygen that will be produced as a result of the reaction between 2.04 moles of sulfuric acid with an excess of potassium dichromate. Now, let's come to part B. Part B states that you have to calculate the mass of the reactant left unreacted. So you already know that the excess reactant is the reactant that is left behind. Some of the amount of the excess reactant is left behind after the reaction is complete. The limiting reactant is consumed completely. So we already know that sulfuric acid is the limiting reactant and potassium dichromate is the excess reactant in this case. So it is understandable that potassium dichromate would be left behind as a result of complete reaction. So we have 2.04 moles of sulfuric acid that are reacting with 0.68 moles of potassium dichromate. We have done the calculations already. So again, we come back to that calculation. And if you remember, when we did the calculation from sulfuric acid, I'll show it to you again. We found out that what we actually need is 0.51 moles of potassium dichromate, and that was the requirement, but we had 0.68, and that is why we decided that it is an excess reactant. But let me do it again for you. So from balanced chemical equation, we know that 4 moles of sulfuric acid will react with 1 mole of potassium dichromate. So 2.04 moles of sulfuric acid will react with 2.04 divided by 4, and this is equal to 0.51 moles of potassium dichromate, and this is what we have done already. Now this is the requirement, and what we have are 0.68 moles. What would be the difference? So the number of moles of unreacted potassium dichromate would be, what is reacted is 0.51 moles of potassium dichromate have reacted, and what is left behind is the difference between what we have and what has reacted, and this is equal to 0.17 moles. The question states that we have to calculate the mass of the reactant left unreacted. So you can convert moles into mass by multiplying it with the molar mass. So 0.17 multiplied by the molar mass, that is 294. We already know that, and this is equal to almost 50 grams, that is 49.9 grams of potassium dichromate. So this is how you can apply the concept of limiting and non-limiting reactants in stoichiometry to calculate the amounts of reacted and unreacted reactants, or determine the amount of product that would be produced as a result. Next is example 1.7, and the question states that magnesium metal reacts with sulfur to produce magnesium sulfide. How many grams of magnesium sulfide can be made from 1.50 grams of magnesium and 1.50 grams of sulfur by the reaction magnesium plus sulfur leading to magnesium sulfide. So let me write down the balanced chemical equation that is already given. We have magnesium metal reacting with sulfur to produce magnesium sulfide. So we are required to determine the amount of magnesium sulfide that is formed as a result of reaction between 1.50 grams of magnesium and 1.50 grams of sulfur. Again, first we have to find out the limiting reactant and then do the calculation. Remember, when you're required to calculate the amount of product that is formed, you will do it from the limiting reactant, from the amount of the limiting reactant that is given to us, as we did in example 1.6. So let's see which one is the limiting reactant. So in the solution, first we have to write the given data, and the given data is the amount of magnesium and sulfur in grams. So magnesium is equal to 1.50 grams and sulfur is equal to 1.50 grams. So the number of moles of magnesium would be the mass in grams, that is 1.50, divided by the molar mass of magnesium, that is the atomic mass of magnesium, and that is 24, and this is equal to 0.06 moles of magnesium. Now to find out the number of moles of sulfur, this is equal to the mass in grams of sulfur divided by the atomic mass of sulfur, that is 32, and this is equal to 0.047 moles. So from balanced chemical equation, we know that 1 mole of magnesium reacts with 1 mole of sulfur to give 1 mole of magnesium sulfide. Here we are given 0.06 moles of magnesium. So for a complete reaction with 0.06 moles of magnesium, what we need is 0.06 moles of sulfur. But what we have in hand is 0.047 moles of sulfur. So the requirement is more than what we have. So we have lesser amount of what is required for a reaction with 0.06 moles of magnesium. So that means sulfur is the limiting reactant. Or you can do it in another way, that for 1 mole of sulfur, we require 1 mole of magnesium. So for 0.047 moles of sulfur, we would need 0.047 moles of magnesium. But what we have is 0.06 moles of magnesium, that is in excess of what is required to react with 0.047 moles of sulfur. So again, that proves that sulfur is the limiting reactant. And now we have to do the calculations from sulfur, and that is to find out the amount in grams of magnesium sulfide produced. So again, from balanced chemical equation, we know that 1 mole of sulfur, because we have to do the calculation from sulfur, that is the limiting reactant, 1 mole of sulfur produces 1 mole of magnesium sulfide. So 0.047 moles of sulfur would automatically produce 0.047 moles of magnesium sulfide. But what we are asked to calculate is the amount in grams. So the mass of magnesium sulfide produced is equal to the number of moles multiplied by the molar mass. Now the molar mass of magnesium sulfide is magnesium is 24 and sulfur is 32, so this is equal to 56. So you can multiply 0.047 by 56, and this is equal to 2.63 grams of magnesium sulfide. Right, this is our example 1.7. Next is example 1.8. And it states that suppose 1.87 moles of ammonium chloride were reacted with 1.35 mole of calcium hydroxide. How many grams of calcium hydroxides are left unreacted in this reaction? So again, it's a matter of finding out or identifying the limiting reactant first, and then of course we will know which one is the excess reactant, and then we can calculate the amount of unreacted reactant present after completion of the reaction. We have done this already in example 1.6, so let's do it here. So the reaction is between ammonium chloride and calcium hydroxide. Let me write down the balanced chemical equation for that. So we have calcium hydroxide, and this is the formula of calcium hydroxide, and it is reacted with the ammonium chloride to give, it's a double displacement type of reaction. So we will have calcium chloride produced as a result along with the formation of ammonium hydroxide. So we have two hydroxyl groups on the left hand side, so we should have two hydroxyl groups here as well. So you write 2 here, and that makes 2 ammonium ions here, and here we should have 2 ammonium ions as well. So you write 2 here, that makes it 2 chlorines here. We already have 2 chlorines here and 1 calcium, so it's a balanced chemical equation now. So we have to find out the limiting reactant first, and then calculate the amount of unreacted calcium hydroxide. But the answer is already in the question. The question that is asked is how many grams of calcium hydroxide are left unreacted in this reaction. So that already proves that calcium hydroxide would be the excess reagent or the excess reactant left behind, and ammonium chloride should be the limiting reactant. But let's calculate, or let's identify the limiting reactant first. So what we are given is the amount of ammonium chloride and the amount of calcium hydroxide. So we have 1.87 moles of ammonium chloride, and we have 1.35 moles of calcium hydroxide. So from balanced chemical equation, we know that 1 mole of calcium hydroxide reacts with 2 moles of ammonium chloride. So if we have 1.35 moles of calcium hydroxide, it will react with 2 into 1.35 moles of ammonium chloride, and that is equal to 2.70 moles of ammonium chloride. So what we need is 2.70 moles of ammonium chloride, but what we have are 1.87 moles of ammonium chloride, which means that ammonium chloride is present in a lesser quantity than what is required for a complete reaction with 1.35 moles of calcium hydroxide, which means that ammonium chloride is the limiting reactant and calcium hydroxide is the excess reactant in this case. And that is what we were given actually already in the question, but we just confirmed it from our calculation that calcium hydroxide is the excess reactant. So for a complete reaction of ammonium chloride, that is 1.87 moles of ammonium chloride, how many moles of calcium hydroxide would be required? That is what we have to calculate first, and then calculate the amount of the unreacted calcium hydroxide. So for a reaction between 2 moles of ammonium chloride, we require 1 mole of calcium hydroxide. This is what we know from the balanced chemical equation. So for 1.87 moles of ammonium chloride, we would need 1.87 divided by 2, and this is equal to 0.935 moles of calcium hydroxide. 0.935 moles of calcium hydroxide will react with 1.87 moles of ammonium chloride, but what we are given are 1.35 moles of calcium hydroxide. So 0.935 moles will react with 1.87 and the rest will be left behind. So we have to calculate the difference of 1.35 and 0.935. So let's calculate the difference. Unreacted moles of calcium hydroxide are 1.35 minus 0.935 is equal to 0.415 moles of calcium hydroxide. But we are required to calculate the mass in grams. So the mass of unreacted calcium hydroxide would be the number of moles multiplied by the molar mass, and you can calculate the molar mass from the atomic masses of calcium, oxygen, and hydrogen. So calcium is 40 and oxygen is 16 multiplied by 2, that is equal to 32, and there are two hydrogens as well, so this is equal to 74. So 0.415 multiplied by 74 is equal to 30.7 grams of unreacted calcium hydroxide after a complete reaction between calcium hydroxide and ammonium chloride. So these were some of the examples from your book regarding stoichiometry, taking into account the amounts of limiting and excess reactants given in the problem or given in the reaction. We'll discuss the next topic, that is the last topic in this chapter 1, that is theoretical yield, actual yield, and percent yield in the upcoming lecture. So stay tuned and thank you so much for now.